Welcome to the next set of notes for Math 135 at CCD. In this section, we're going to go through Module 5, which is looking at a linear relationship between two variables. Please know that a lot of the things we're going to cover in this section are very reliant on your calculator. So while we are going to be going through a lot of this stuff in these notes, all of the calculations I'm doing are on my calculator. So you will need to watch the Module 5 calculator video as well to understand how a lot of these numbers came out for these notes. The first thing we're going to look at is with a scatter plot, which is a visualization of two variables on the same graph, looking at if there is a linear relationship between them. So what we have here is we have 5 different graphs. The first two are a linear relationship because if I draw a straight line through the graph, it hits most of these points, either straight up or straight down. However, if I try and draw a line through these points, we see that we've got a distinct curve, and then this last one, there's not really a line that I can draw through the graph. So these are 2 examples of linear relationships and 3 examples of nonlinear relationships. We want to focus on relationships between two variables that are linear, so like these first 2. So once we think we have a possible linear relationship by looking at the scatter plot, we can then calculate a correlation coefficient. The correlation coefficient gives us a numerical value to describe how strong the linear relationship between two variables is. We have here some examples of graphs and what their correlation coefficients are. Let's do blue. So this first graph here, we have a correlation coefficient of 1. That means there is a perfect positive linear relationship between these variables. That means if I draw a line through the graph, if it were straight, it would hit all of the dots perfectly. This second graph here, we have a strong positive linear relationship, which has a correlation coefficient of 0.9. That means I can draw a line through the dots. I hit most of them. It's definitely a straight line, but I'm not necessarily hitting every single dot along the way. The third graph that we have here, this is a moderate positive linear relationship. This particular graph has a correlation coefficient of 0.4. Here we can definitely still see that it's going in a straight pattern, but when I draw the line, I'm definitely going to be missing a lot of dots along the way. So these are 3 examples of positive linear relationships. Now we're going to look at 3 examples of negative linear relationships. So the first one we have here is a perfect negative linear relationship. This one has a correlation coefficient of -1, so it's perfectly negative. I draw my line through it and I hit every single dot along the way. The second one that we have here is a strong negative linear relationship. This one has a correlation coefficient of approximately -0.9. So I draw my line through there and it hits most of the points, but I missed quite a few of them, partially because my line wasn't very straight. Neither is that one. Okay, but we still missed some of the dots, but it looks pretty much like it's in a straight line. The next one we have is a moderate negative linear relationship. This one has a correlation coefficient of -0.4. So again, I can draw my line. It goes pretty straight, but it does miss a lot of the points. And then finally, we have 2 nonlinear relationships here. The first one that we have here, our correlation coefficient is close to 0, and there's not really a line that I could draw through this at all. The dots are pretty much random. There's just really no distinct pattern. The second one, my correlation coefficient, again, is close to 0, but this time if I draw a line through my data, I can definitely see that there's a curved pattern. A curve is not a linear pattern, it has to be a straight line. So I'm going to come down to the bottom because I didn't really leave myself a ton of room for these. And I'm going to draw a line to describe this relationship between what the correlation coefficient is telling you and what that means in terms of how strong of a linear relationship do you have. Now the correlation coefficient, that is one of the things that we're going to be using our calculator to calculate for us. If you look at the equation for it, it is a beast. It is much more difficult even than the standard deviation equation was. So we are not going to do this by hand ever. But we do need to understand the relationship between the number that we're being told and what that means in terms of our data. So correlation coefficient can range from -1 to +1, and 0 is in the middle. So starting on the negative side, if you get a correlation coefficient of -1, that means you have a perfect positive linear relationship. I'm sorry, a perfect negative. Perfect negative linear relationship. If you have a value between, actually I don't want that color, I'm sorry, -1 and -0.7, this means that you have a strong negative linear relationship. So it's not perfect, it's not the perfect line where you can draw through every single dot, but you're gonna hit most of the dots in that single straight line. The third one we have is a moderate positive, so that's anything from -0.3 to -0.7. So what's here in blue? This is going to be the moderate negative. And then finally, anything from -0.3 to 0 is no linear relationship. So that's the negative side. Now the positive side is going to be very similar. It's just going to be mirrored. So anything from from 0 to a positive 0.3 is going to be no linear relationship. Anything from 0.3 up to 0.7 is going to be a moderate linear relationship. And then anything from 0.7 up to 1 is going to be a strong positive linear relationship. And then a correlation coefficient of exactly 1 is going to give you a perfect positive linear relationship. So this is the relationship that we see between the correlation coefficient that we're going to calculate in our calculators and what that means in terms of how straight of a line do we have, or how linear of a relationship do we have amongst our two variables. So here is that diagram to describe what we were seeing in the graphs up here, up above. So for the rest of this, we're going to look at an example. What I have here is a sample of 5. We looked at 5 households. We asked them how many people live in the household and how many times they eat out in a month for this data set. So the first thing we're going to do is we're going to draw our scatter plot. It does not have to be perfect, just as close as you can get it. So we're going to start with a horizontal and a vertical axes. Our independent variable is going to be the household size, so I'm going to label that down here. And then the dependent variable is going to be the number of times they ate out. So I'm going to label that here. So we see that our household size goes from 1 to 7, and our number of times they ate out goes from 4 to 18. So what I'm going to do is I'm going to put dots on this graph to represent each of these pairs. So if you think of it this way, the household size is going to be like my x coordinate, and the number of times they ate out is like the y coordinate. So this gives me an ordered pair to plot each of these points. So my household size of 1 and the number of times they ate out is 18. So there's my first point. It does not have to be perfect. And then we have a household size of 3 and they ate out 13 times. We have another household of size 3, they ate out 9 times. We have a household size of 6, they ate out 6 times. And then we have a household size of 7, which ate out 4 times. So this is an approximation. If you want to go through and put the actual tick marks in there and for the size and the number of times they ate out, that's fine. If you want to estimate it kind of like I did, that's fine as well. So this is the first thing we want to do when we're looking at, is there a relationship between these two variables? So by plotting these points, I can see now that if I take my green, I can kind of draw a straight line through most of these dots. Again, mine's not a straight line. It should be. Okay, so that makes me think, okay, maybe there is a linear relationship happening here. So I'm going to proceed to calculating my correlation coefficient. So the correlation coefficient is going to be calculated in our calculators, and I will go over that in the Module 5 calculator video. And when we do that, we get a correlation coefficient of negative 0.9456. So negative 0.9 is very close to negative 1. So this tells me that there is a strong negative linear relationship It also tells me that as the household size increases, they eat out less times per month. So this tells me, this negative 0.9 tells me that as I moved higher along my independent variable, I saw a decrease in the values of my dependent variable. So that's all I've stated here. As the household size increases, which was my independent variable, they ate out less times per month. That was my dependent variable. And it's less because we saw a decrease. So now that we have our correlation coefficient and we see that we have a strong relationship, we're going to go ahead and find an equation that models this relationship. So if I still had this drawn in here, and I can redraw it in, if I still had my green line, what is the equation of this green line that best fits my data? And there's a lot that goes into this. It's called the least squares regression line. Okay. And you don't necessarily need to know all of that. All you need to know is how to find it and how to interpret all of it. So a linear equation from back in our linear algebra days follows the form y equals mx plus b, where m was the slope and b was our y-intercept. In stats, our equation is very similar, it's just a little bit different. Now we're going to say y hat equals a plus bx, or you could also say y hat equals ax plus b. In this case, and I'm going to focus on the first one because this is the way that your book words everything, this y hat means we're making a prediction. A is now our y-intercept, and b is our slope. So it still follows a very similar form, but now our y is actually, we're predicting what would the number of times they ate out per month be with X number of people in the household. So we're going to go ahead and find the linear equation for the data for this first example that we're working with today. And again, this is found in the calculator, and I will go over that in the calculator video. So from that, we get an equation of y hat equals 18.6667 minus 2.1667x. So now here we have our y-intercept is 18 and our slope is negative 2.1667. So what that means, an interpretation of these is if, what color did I do that in? If we had a household of size 0, so if x equals 0, we would expect the family to eat out 18 times per month. So they would eat out 18 times per month. And then our slope, we can say that as we increase the household size by 1, so if I plug in 1 for X, that'll decrease the number of times they eat out by 2.1667. So as the household size increases by 1, the family eats out 2.1667 times less per month on average. So that is how we can interpret what this y-intercept and what this slope is telling us. Now, in the case of this y-intercept, it doesn't make sense to have a household size of 0. If there's no one in your household, if there's no one in your family, then you can't eat out 18 times per month with 0 people. But in other circumstances, it will make sense for you to have an x value of 0. For instance, if you're looking at the length of a child in relation to how old they are. If x equals 0, that means that is the child's length at birth. So their age is 0, which means that is how long they were when they were born. So there are cases where interpreting the y-intercept doesn't quite make sense to us in a realistic method, but there are other cases where it does. So now we said that this equation is going to give us a prediction of something. So we're going to use this equation to predict how many times a family of 4 eats out. Coming back up to my data set, we didn't have any data on a family of size 4. Most families that I know have 4 people in them. My family growing up was a family of size 4. My sister's family is now a family of size 4. So I'm really curious as to see how many times a family of size 4 eats out according to my equation. So what I'm going to do is I'm going to take my y hat equals 18.6667 minus 2.1667, and I'm going to replace the x with a 4. And now I'm going to use that to determine how many times this family eats out. So 18.667 minus 18 minus 2.1667 times 4. And I get 9.9999. So according to this equation, a family of size 4 eats out 9.9999 times per month on average. Okay, so we can predict for a family of size 4 by replacing x with 4 and then just plugging this equation into our calculator. Now the final thing we're going to look at with this is a residual. So the residual is the difference between what was observed and what we predicted. So a residual is calculated by taking the y that we observed and subtracting the y that we predicted. I'm sorry, I think I have that backwards. And I do this every semester. Bear with me, I'm sorry, guys. As you can see, even I get this stuff confused sometimes. Y observed minus Y predicted. Yes, I am correct. I apologize. I really thought I had it backwards. Okay, so this Y observed is going to come from our table of data. Okay, so this is going to come from our data, and then this y hat is going to come from our equation. So now we're going to go ahead and find the residual for a household of size 7. So first thing I need to do is I need to find what y hat is for a family of size 7. So 18.6667 minus 2.1667 times 7, which gives me a number $3.4998. And now I want to go find my y observed from the table. So I'm going to go back up to the top and I'm going to look at my original data table. And I'm going to find the household of size 7. And I'm going to look at how many times did that household eat out. So a household of size 7 ate out 4 times. That's what I observed when I collected my data. So 4. So now I'm going to use my residual equation, and I'm going to say, okay, the residual is equal to what I observed minus what I predicted, and that gives me 0.5001.002. So this value right here is my residual. And this tells me what the difference is between what I observed and what I predicted. So then what we can do with this residual is we can say whether or not this means our equation is over or underestimating the response variable for this particular number. So for a household of size 7, this equation is underestimating, because the result from our residual was a positive number. If you calculate the residual and you get a negative number, that means your equation is overestimating. And it's very important that we have these over and underestimates as small as possible, and that's part of what goes into forming this equation that we found up here. So in review, we looked at how to determine whether we have a linear relationship by first looking at the scatter plot, which we did with our example, and then calculating the correlation coefficient. We then looked at finding the linear equation for the data and how to interpret the y-intercept and the slope. We used our equation to predict for a family of size 4. And then finally we looked at the residual, and we found the residual for a family of size 7. And then the bottom thing I have in these notes is that relationship between what the correlation coefficient is and what that means in terms of whether your linear relationship is perfect, strong, negative, or non-existent. So that's it for Module 5. Make sure you go and watch the calculator video now, where you will see where I found this R value, the slope, and the y-intercept values that I found in these notes. So go watch that now.